Okay, let's get started. So Tuesday, I showed you guys the memory map and didn't work, and that was because of a permission issue. So we updated the system a little bit. If you go to the permission process map, which we can say process map and so forth, so 2-bit. So previously, this application, the owner of that is root. Now we change it to CTF. So now you will be able to see its map. So let's run this program on one terminal, and on another one we just do let's see, it has a PID of 58. So we just do a pmap -x 58, and you will be able to see its memory map here. Okay? So previously, we didn't show this because we don't have permission. And a year ago, in the older Ubuntu, actually, even if this application was the owner is root, everywhere else would say it's met. So obviously, Ubuntu updated its permission again. That's why we have to update this app a little bit. So we were talking about system calls last class, and I believe we were here. Let's start from here. So now we are looking at 10 instructions here, and those 10 instructions are actually making a system call in x86 architecture, and we are trying to figure out what those 10 instructions do. And in this class, we will do a lot of disassembly, give you an app, and you're going to read the disassembly. And this is one piece of code, which is a very simple one, so we start from here. Okay, so let's take a look at those instructions one by one. So the first instruction here is XOR EAX EAX. So XOR is exclusive OR operation. And the first one, the first operand is destination, the second one is the source. So in this case, we're doing exclusive OR operation on two values, and both of them are stored on EAX. So it's the same value. So what do you get when you do an exclusive OR operation on the same value? You get 0, right? So basically, this instruction is equivalent to reset EAX to 0. Okay. Now after that, the second instruction is a push EAX, and the push is to push something onto the memory, onto the stack, and the stack is pointed by the register ESP. This is the register. So basically, what we're doing is we're putting the value of EAX, which is 0, onto the stack. So here there will be 0, and the ESP points to that value. Then we push another 2 tiny weird numbers. Okay, we're pushing through those numbers. Later we'll figure out what they are. Right now they just look like 2 numbers. After that, we're moving the value in ESP to EBX. Both of them are registers, right? So which means we are copying the value in ESP to the register EBX, which means after this EBX, we're also point to this address. Okay. Now after that, we are pushing EAX again. The low one has changed the EAX so far over here. So EAX still has a value of 0. So we'll say another 0 here. Then we have another, we push the EBX as a value to here. And the EBX, we know that points to here. So the value here will also points to here. Then move ESP to ECX. Then most importantly, the last two instructions, we are moving the value B, which is the decimal number of 11, to the register AL. And the EAX was 0, okay? So it's 32 bits, all 0. Now we are only changing the last byte of it, the least significant byte. So after all, its value will be just a B. Then we have the int instruction. I told you before, this is a system call instruction. So here we're making a system call, right? So what exactly we're doing here is we are making this system call for the EXE, which is to execute a program. If we use man2 EXE, we will get this manual. Now for this manual, we can say this system call, even though this is written in C format, this is a system call. This system call takes 3 arguments. The first one is a file name, right? The program you're trying to execute. It's a file name. It's on the file system. The second one is an array of pointers for the arguments. So the program we are executing is maybe this one, and we don't have an argument, right? So the default argument will only be the first command line argument will be the name of the program itself. The second argument will be the second command line argument. If you do not give that, then you just give a 0, right? Then in this case, we'll give a 0. Then the third one is the environment variables. In this case, we don't need them, so we also give a variable. So what we saw just now is equivalent to this say function call, bin sh address of this string and 0. So how did we get the string? We didn't say the string there. This string is actually this very weird 2 numbers. Okay, those are ASCII numbers, the ASCII values of that string. So here we have so we are pushing those 2, which means this one will be at a higher address, this one will be at a lower address. Okay, so we're pushing this one first, pushing this one next. So every time we push, the ESP decrements, right? But if you're looking at a string, that string, the first character, the first letter, obviously is at a lower address. So what is the lowest address of this thing, right? This thing, because this is little endian, the least significant will go to lower address. So the first character here is actually 2F. Okay, so the one is 2F. If you go to the ASCII table, you say 2F will be here. 2F is a slash, okay? A /. So the program we're executing is actually /bin /sh. Okay. But there could be multiple slashes. So in Linux systems, if you have /bin, that is equivalent to /bin. Okay. Then the next letter is 62, which is here. No, sorry. 62 is here. This is a hex value. It's B. Okay. So the third one is I, which is 69, which is I. Next one you can imagine is N. After that, you have another, then you go here, which is another 2F, which is another slash. In this case, we actually use the 2 slash here, //. So I can show you this in our system. So like I said, in Linux systems, if you have 1 slash or have 2 slashes, they're the same thing. Let's say, if you say the /bin, you go to /bin. If you go to, let's go back. If you go to /bin, it's actually the same thing, okay? You still go to the bin, okay? So the reason we're using 2 slashes here is because we want to fill the whole register. The whole register is 4 bytes. We don't want to have a zero there. There are many reasons we don't want a zero there. Okay. That's why we have two slashes to F here. Now after that, obviously 73 should be S, and 68 in hex will be H, right? So that is actually the string. The file name we're going to execute. The program we're going to execute.
So why do we have two pushes? Is it like dividing?
Because this is 32-bit.
Okay, so
You don't have a
the
push
string
to push
divided
8
into
bytes.
two parts.
Yes,
Okay.
yeah. You don't have
And it just runs automatically, right?
what do you mean automatically.
Because we have a string, but like there are two.
So
Can we?
for the computer,
Mhm.
it doesn't know this is a string, right?
Uh-huh.
For the CPU, it only knows I'm pushing the value. The
Uh-huh.
CPU doesn't care if this is a string or not
Uh-huh.
at this level. Yeah.
Okay, I got it.
Yeah.
Thank you.
So if you want to know more about system calls, you will look up this table, especially in this class, we were starting 32-bit and 64-bit, and no one could remember those system call numbers. And it's not necessary to remember that, right? So just to go to that website, then look for the system call, what parameters you are going to use to make that system call. Okay. So here is another example. This is the 64-bit version of almost the same system call. But the syntax of this is a little bit more flexible. First of all, at a 64-bit, we do not use stack to pass parameters. Okay, the first 6 parameters we just use registers. For system calls, we also use registers. Right. So first of all, is the system call number is changed. In the 32-bit, the system call number is 11, or B in hex. In 64-bit, is actually 59 in decimal. Then 59 is actually 3B in hex. Then you need to set other registers accordingly. The first register will be RDI. That register, you're going to set the file name, which is a pointer to the string of the file name. The second register will be the argument array. The third one will be the environment variable array. But for both of those, we don't really need anything for now if we just want to shell, right? So in this case, we first push AX here, then we do an inclusive OR to RDX. So RDX will be 0. After that, we clear RSI because those are the registers we are going to use here. Those two, right? We want to set them as 0. So this one and this one will be 0. Those two will be 0. Now after that, we move this string's address to RBX. Actually, we're moving a string. In this case, we're moving a string here. Yeah, this is very interesting. Now we push RBX. No, this one is the address. Yeah, this is 64-bit syntax. This one we're moving this string's address to RBX. Then we'll push RBX to the stack. Then we'll push RSP to the stack. Then pop RDI. So this one, we're actually moving the value of RSP to RDI, right? We push this to stack, then we pop to stack. But maybe we do not find an instruction to directly move this. That's why we're doing this. Okay. Now after that, we just move the system call number 59 to AL. Then we make the system call. And here we're not using int 80. Instead, we just use the system call instruction to do that. So most likely in this class, you will make some small changes of this kind of piece of code. Most of the cases you will directly use them. Right? You don't need to change. But in share code module, we're going to make some small changes. Yeah, of this. So I recommend you guys to read this book, the Linux System Programming. In this book, you will learn a lot of C interfaces and also system interfaces provided by Linux and also Unix-like systems. Okay, another piece of background knowledge is the environment and shell variables. So in Linux and Unix-like systems, system environment variables are is a set of dynamic named values. In Windows and other systems, we also have this. They are stored within the system and are used by applications launched in shells. So when you create a new process, the operating system is actually copying those named values to the address space of that process. And we're going to see a demo of that. So those environment variables, they have this kind of format. Name equal value. That's a format. So I guess many of you are familiar with this from Windows or Mac or any other systems. And we're going to utilize this in our class. So this whole thing is actually a string, okay? Every environment variable is actually a string. The string has three parts: the name, equal sign, and the value of them. So the name of those variables are case sensitive. Usually we use uppercase, but it's actually case sensitive. And the multiple values must be separated by the column character. If you use the pass before, right? We can do a echo that. So pass is an environment variable which is set on this platform. So when you run any program, you do a ls, you do a ps. The shell is looking for that program ls or ps from those paths in this order. Okay, it's first looking for whether we have this app ls under this folder. If not, it will go to the next folder, then other folders. Okay, and the different folders in this case, they are separated by a column. Right? So there is no space around the equal sign, right? It should be name, equal sign, and value. No space. So environment variables are set system one, and they are inherited by all new processes, child processes. So, but shell variables are variables that only apply to the current shell instance. The shell we're using in the platform is the Z shell, which is very convenient, and you can set shell variable just for this Z shell. But we're not using this much in this class. There are some common environment variables that the system always have, like user, so who is the currently logged in user, what's a home directory, what's a share we're using, what's a path, we can show you that. So we can take a look at some of this. We can just use the echo, the $sign, the name of that. For example, we can do a $sign home. It shows me for the current user CTF, what is the home directory for that user, which is /home/CTF. So we can say with the user here, it's CTF, right? Then there, what others? Shell. This one is interesting because we are not using a default shell here. So the shell, we're using a bash here. Oh, I saw we installed a dash. Okay, on this platform, we didn't install that. We're still using a bash here. There are several commands you can use to change and view environment variables. EVN is one of them. You do a EVN, you say all the environment variables here. So EVN, you say all of them. Right? Just one here. You say all of them. They are shell, Emacs, directory, even display colors, all kinds of preset, predetermined environment variables are here. You can also use the print environment variable to show a very specific one. You can do this to show user, the uppercase user. Okay, and also I just showed you, you can also just do a simple echo here to do that. Value will be a variable. Yeah. Should be $sign in this case. We get the same thing. There are other commands to do set, onset, or even export. So in this class, we will use the export command to introduce some environment variables in a program. So here we're talking about the environment variable names and how they are set in the operating system, right? From a user's point of view. But when you actually run a program, it will create a new process. And that process will also have the access of those environment variables. So those are actually stored by the loader, by the operating system, in the address space of the program, along with the command line arguments and everything else. So we can say a simple demo here. We can go to like any program here, say, don't need too much here. So now we have a simple program is process map. We can do a GDB here. This is to debug this program. So when we debug this, a GDB is a tool we are going to use a lot in this class. We set a breakpoint. We set the breakpoint main. So now we have a breakpoint at the first instruction of the main function. Then we just run this program. Now, okay. Yeah. So now we are running this program, right? We're actually, right now, we are about to execute the very first instruction of the main, right? And main is what the developer developed. So before this, a lot of pieces of code has already been executed, right? So I told you main is what you develop as a C programmer. But before that, the C library already did a lot of initialization, load memory, load libraries to memory, all kinds of stuff, right? So at this point, the environment variables, they are already put on the stack. They're somewhere on the stack, and we can examine them. Right? Let's say we want to examine. So X is the command to examine something. So where is the stack? How do we find the stack? Right? Yes, the stack pointer points to the stack, right? So we can examine, let's say we examine 40 strings here at the location of the stack pointer, ESP. So if we keep doing that, we're going to examine higher address. Right? So if we examine this, eventually we should be able to find those environment variables somewhere on the stack. I don't know where they are. Let's say what I do, I use the string. Oh, I'm using too small to maybe 500. So we see a lot of just one byte here. That's because it's 0. Right? We're keep going, but we're going a very those were the instructions, and the instruction. Oh, I think 500 is not big enough. Let's do 5,000. Oops, no, zeros memory. ESP, maybe the main function. It can. Okay, let's revisit this one later. Okay, the last piece of background knowledge is the air file. We actually talked about this, so I will let's say if there is anything important we have to cover here. I want to cover a little bit about the header. So this is a file. This is an L file, and the L file has different modules. There is a header. There is a program header, executable header. Then there are different sections and section headers. The executable header actually tells you what program this is and what architecture this is compiled for. It could be x86, it could be ARM, and the executable file type could be executables, could be object files, dynamic memories, dynamic libraries, and we can use the tool I showed you last class, read-elf, to show that, to give you a human readable output. But they are basically just numbers in the header. So this is what we saw in the last class. So the sections, they are for the code and data in L file, and they are logically divided into continuous but not overlapping sections. And the structure of each section depends on the content of that section. And the division into sections is intended to provide a convenient organization for use by the linker. Okay? You have multiple files, and the linkers is going to merge them into one file, and the linker will read the sections and merge them. So using this command, we can read each section described by the section header. So the section have several different types. Here, the type could be program bits. So this is basically the instructions. It could be symbols, symbol tables. It could be strings. This is string and relocatable, dynamic symbols, and other things. Then there are also flags, like the permissions. Those are executable instructions, and those are writable regions, sections. So those are flags and types. So if we use this read-elf -s command, then we can get the sections of L file. Some of them we are all kind of familiar with, like dot text section, right? So that is where the program is. So that's why its type is program bits. Then there are other, and this is where your program is, and there are other parts. We can say they're also programs, program bits. So most of them are say library functions, the libc function. You didn't program them, but they are also programmed, like the init, plt, read only, those things. Also GOT. Then we have a .data section, the SS section. We already started that in the last class. So some of the important sections, .ebit is executable code that performs initialization task, usually part of libc. Really, code runs after the main program completes. .text, where your programmer will go, .text. .ro data, read-only data. We talked about this already, so we'll skip this. So in modern systems, we actually use a technique called lazy binding so when a binary is loaded into a process for execution, the dynamic linker is called dynamic linker, means it will resolve things at runtime. The dynamic linker will resolve reference to functions, for example, say library functions, the functions you didn't develop in shared libraries. Then resolve here means find the address of those functions. So eventually at the CPU level, everything is the address. You are on the memory. Okay, memory is marked by different address. You want to call a function, you're actually asking your CPU to execute at that function's address. So you need to find the address. And the linker's job is to do that. And the dynamic linker is going to find those addresses for you. But imagine you develop a C program. Your C program will load the C library. The C library has thousands of functions, thousands of APIs. Your program could be very simple program. You are just using one or two of those APIs. You're not using all. So it's not necessary for the linker to find the addresses of all those C library functions at the beginning of the program. If it finds that, it takes maybe 5 seconds. It's a waste of time because you're not going to use that, right? So that's why we have the technique called lazy binding. So when your program is making an API call to the functions, the linker will find the address. So the first time you make a call to a function, you find the address. Here's the address in a table. So the second time you call that, you still know that address. Then for all other, maybe thousands of functions which your application do not call, we never know their address. And we don't never need to know their address. So save a long time. So this is called the lazy binding. And we can, and the lazy binding uses several tables to do that. And those are the tables we can also attack in this class. This is actually achieved by two tables or sections. One is called the procedure linkage table .prt, and another one is global offset table GOT. And the GOT actually has a subsection for the PRT. So it will be .got.prt. So that section actually will be the data section. I think I have a demo for that. So let's take a look at the figure. Let's say this is your code. This part is your code. This is a library.prt table. This is a data section and the got.prt table. Your code, this is the main function. The main function makes a C library function call, which inputs. So the printf will eventually call puts, right? And puts eventually will call the system call write. So here, let's say this is printf or puts. So this is the first time you make this function call to puts. So the program doesn't really know where the function address is. It doesn't know yet. Instead, it will jump to this PRT table, which you didn't program, part of the C library. This table will try to find the address of puts in a table. This is code, this is table. If there is no address in the table, then it knows that I don't know the address yet. Then it will go to a default stop here, which will try to resolve the address and put the address here. Then make a function call to this address again. So at a very high level, what you will say is, if we run a program twice, we run the same program, and the same program calls the same function twice. You will say that the first time it calls a function, it behaves differently than the second time it calls a function. The first time it calls a function, it doesn't have the address. The second time it has. So we have a demo for that. And we're going to use the lazy B challenge to do this. So let's assemble it first. what I want to show you is actually this part. This is the main function. The main function makes two function calls, printf. Both of them eventually becomes puts, okay? Two puts. And I'm going to show you that the first time and second time we call it, they are actually at different address, behave differently. That's because the first time we call it, we will actually resolve the address, and the second time we already know the address. So what we can do is we'll also use this opportunity to learn a little bit GDB here, right? So we debug this program, use GDB. We run this, we set a breakpoint at the main, and for that. Then we do a disassemble, then we can, we need to run the program first. Now we run the program is running, and we do a disassemble here. Now we can say the instructions of the main function. We will skip those parts, okay? Instead, we will set a breakpoint at this instruction and this instruction, those two instructions. How do we set a breakpoint? We get the address of this. Then we do a B star this address. That's the syntax. Then we set a breakpoint at here. Then we set up another breakpoint at this address. We set two breakpoints. Now we have
Quick question, how are you pasting in the address?
you do a Control Alt and V.
Oh, okay.
Yeah, in terminal, that's how you
Thank you.
copy things. Yeah. That's how you paste the thing. Yeah. Copy, I just use the mouse to do that. Yeah. Are you able to copy?
I am not, but I'm not
Good.
sure what's happening yet.
So did you copy or
I did right click, copy,
okay?
then I do Control Alt V.
Not working?
Now.
Oh, maybe Control Shift.
Oh, yeah.
Yeah, it's Control Shift. But yeah. For me, it's just natural, so I don't really remember which what. Yeah. Okay. Now we set a breakpoint here, right? So now what we want to do? We want to skip those instructions. We just want to go here, right? So the command we are going to use is C, means continue, right? We just do a C here, GDB, we do a C, now we continue. Running, now we are at the breakpoint 2, right here, right? Now we are going to step into this call and we will record that address. Now we're making the same function call twice. Supposed to be the same address. Let's say if it is the case. Right? So if we do a step in, which will be SI, which means step and instruction. I here in instruction. If we do that, we are at this address. We're at this address. You can see this is a very small, short stop here. It's not a full function, right? So here is 4070. Okay. This one we keep doing SI. Now we are at this line. Then we do a SI again. Okay. When we are here, we're not in any function anymore. This address is 4040. We're not in any function. So when I use a command disassemble, GDB could not be able to disassemble this because this command can only disassemble functions. But we can still say the instruction here use other command like exam command. We can do an exam, 10 instructions. Instruction is I here, and we are examining from the IP address place. So we do this, we still say the instruction here. Okay, this function doesn't have a symbol. That's why we are not, the GDB is not able to disassemble this, but you can say it's actually also looks like a function. So this is the address. This is the first time we try to call this, we get it here. And this doesn't look like the puts function, right? Anyway, we continue execution. So if we continue here, where do we get?
breakpoint.
3.3, yeah, because we have a breakpoint at the way,
Okay.
yeah, the next breakpoint, right? So now we finish that first write to the terminal, which is the first call to printf. Now we are in the second call. To show that we're actually here right now, the second call to puts. And if we do a SI here, we go to the same step. But if we keep going, so far it's the same. Move one more step. Oops, should do SI here. So now it's different, you see? This time, we didn't go to the previous function with no name, right? Previously, we call into a function that we don't know its name. And the GDB couldn't disassemble that, which is this one. We go to this address, this function. The second time we make the function call to the same function, puts, we go to a different place. We go to the function of puts directly. And the function in the C library, its actual name is _gi_io_puts. Because the second time, we already know the address of this function, so we are calling into that. The first time, that piece of code is trying to resolve the address of this and put that in a page, in a table.
Exactly a page fault or is it similar to a page fault?
This is not a page fault. Yeah. So page fault is a MMU hardware feature here. So here we're not using that. So it's just a software layer trick to do this. Yeah. So basically the table has the address of the functions. If the table is initialized to 0 without those addresses, then it knows, oh, I should resolve them. Yeah, there's no page fault here. Yeah.
How will we end up in a place where something data are being the first case is the question mark. How will we end up there? Because everything is code should be done.
No, a lot of first of all, a lot of code there do not necessarily be part of a function. They could be developed in assembly directly. And when you write assembly code, you do not necessarily create a function for that. Second, the piece of code we saw there is very likely it is a function, but the symbols are removed from the binary. So the GDB tries to load the symbol, it couldn't find the symbol. Yeah, so it cannot recognize that. Okay, so this one actually should, yeah, go ahead.
Yeah, so when that happened, was there an exception in the operating system that led to that? Loaded?
No, here also no exception, yeah. So what you are saying is,
Or was there an interrupt? Something that loaded the,
no, here no.
so who loaded the?
The interpreter, the loader, yeah. It's, you can say it's part of the C library, but we saw that there is a libc, there is also interpreter, right? That program is also part of the process, but as a developer, you didn't develop that. Part of the C library, loaded there, and loaded into the address space of the process. So it's not directly part of the kernel. That module will talk to the kernel to do all kinds of things. I guess we will skip the segment part because it's not that important for our hacking. Introduce you some of the tools we are going to use in the class. You already see some of those. File, readelf, strings. Use the strings to do recon. You can find all the strings in a file, okay? No matter what file it is. Let's say we do a strings on this program, the lazy V, and we find there are many strings. So those section names, they are actually strings as well. And we should find the string. The program actually shows two strings, right? When we run this program, it shows two things. It shows first the call to printf, second call to printf, right? So those are hard-coded strings in the program. So if we not encrypt them, then we should be able to find those strings by just using the command strings, right? So let's say if they are here somewhere, we say also see some function names here. And here they are, okay? Those are the strings. So the tool string just do a search in a file and to find strings which is longer than 5 or 4 bytes, I think. Obviously, that's a parameter you can set. You can change it to a longer ones. So string is also a tool we can use to do recon. obj-dump, it will be your friend. GDB, it will be a good friend to understand how program works in the class. IDOT is a professional tool to do hacking, binary hacking. I think there is a free version of it. If you can use that, but the professional version is very expensive. My lab used to have one. Oh, I think we paid like 20K or something for a year. Yeah, for a year of service, we can always use that, but 20K just for the software. Hydra is a tool you can also use. This is free. This is open source by National Security Agency. It's actually pretty good, getting better and better. And another tool I feel quite useful for this class would be Binary Ninja because they have a web version. Okay, they have a web version and it's free. You just go to, Google Binary Ninja. Go to the cloud version, which is free. I don't have an account on this computer, but you can register account. You can load your binary there. Then they can actually do decompiling, which means they will give you a C code. But the C code sometimes have many errors. But they try their best to give you a C code. But I still want you to read more disassembly in this class so you can understand exactly what's going on. I provide a cheat sheet here for GDB and everything else. This is just for reference. You don't need to remember in the CTF or homework. You can just go to this page. Okay, so now, our class ended at what? 4:30. 4:30. Okay, we still have 50 minutes left. Okay, cool. Now we are going to our first hacking topic. So finally, we have get the background out of the way. We should be able to do some hacking now. The first hacking we are going to do is buffer overflow, or it's a stack-based buffer overflow. This is also called a sequential buffer overflow, because most of the cases we are overwriting the stack in a sequential way. So we will talk a little bit about the history of buffer overflow. We discuss the information a say function needs to actually run, different say calling conventions. Then we will try to overflow some local variables. The next class, we will overflow some return addresses to execute a function, and also we try to overflow the return address and execute functions with parameters. Then we were sometimes we do not have the luxury to overwrite the return address, then we try to overwrite something else to achieve the same goal. So the objectives are, you should, after this class, you should be able to understand how stack works in Linux, Unix, and also Mac, Windows, especially on x86, 32-bit or 64-bit systems. Give you a piece of C code, you should be able to identify some obvious buffer overflows. Sometimes it's very tricky, okay? Sometimes it's not that obvious, but at least for this class, the examples I'm showing you, it's quite obvious. then you should be able to exploit those vulnerabilities. You are getting the flags, right? That's a goal, right? You need to exploit the vulnerabilities to get the flags. So a little bit of history about buffer overflow. So this technique was discovered back in the 80s. But back then, not many people knew about this. The very first famous exploitation of this was Morris worm back in the 1988. So Robert Morris, right now he is a professor at I think he's a professor at MIT, and he has been a very successful entrepreneur as well. So back then he was a student in Cornell, I believe. He was a graduate student in Cornell. So he developed the very first computer worm, and that worm exploits a buffer overflow in the Unix boxes and try to replicate itself to other computers. So I think it took down maybe 10% or 20% of the internet back then. Of course, at that time the internet was very small, right? So he was actually convicted back then. Yeah, he was maybe the first computer criminal, technically. Yes. Before he was this famous professor, he made a huge contributions in security, distributed system, OS, many other things, and has many successful companies. He's probably just crossed the river. So, but still back then, not many people know this dark magic, okay? Until 1996, someone used a pseudonym, but you can find his real name right now. It has been like 30 years. So this guy, Alpha1, okay? He wrote an article, and the article was published in a hacker magazine called Threat. So this magazine still exists now, okay? They still publish all kinds of original attacks. So this guy, Alpha1, published this smashing the stack for fun and profit article. And this is the first well-written article explain how buffer overflow works and taught people to do buffer overflow. Before that, not many people can do that. You will be able to do this in several ways, but before that, there's no tutorial, right? And only a very small number of people were able to do this. So buffer overflow, even today, it's a very serious problem. So this is a screenshot I took several years ago. This is published by an organization called MITRE. They publish all kinds of software vulnerabilities, hardware vulnerabilities, and also CWE here is called common weakness enumeration or whatever. So the weakness of software and hardware systems. And in the top 25 weaknesses, you can see the very first one is improper restriction of operations within the bound of memory buffer. So that is actually the out of bound right. That's actually a buffer overflow. The second one is cross-site scripting. That is related to web, which we do not cover in this class. The third one we can say somehow related to binary. The fourth one we will do that. The seventh one use after 3, we're going to do that. Integer overflow we will cover a little bit. The ninth one cross-site request a forgery attack. That's also a web-based. Okay. The 14th one we will cover that. So those are the common weaknesses in the software or sometimes even hardware systems. So this is still a very serious problem. So in my lab, a lot of our research projects are still solving those kind of problems. That's why I call this class the baby step for my research. If some of you want to work with me to do research, this class is a must. Without this class, you will not be able to understand what we do in the class. Okay. So next we talk about the C and C++ functions, how they are implemented in modern architectures, right? So what kind of information do we need to call a function at runtime? I'm not talking about at the developer level. Think about your compiler writer. Okay, what kind of information you need? As a developer, what information you need? You need the function's name. You need to know the function's prototype. That's basically it, right? Yeah, but that's only for developers. If you are compiler writers, that is an interface you provide for the application developers. But how do you actually implement that, right? So at the source code, at the CPU level, there's no concept of name anymore. Everything is address, everything is on memory. So what you really need is, obviously, you need the code, the machine code of that function. You need to place it somewhere. Eventually, you're going to execute that. You need parameters for that function. And every time you call that function, the parameters could be different, right? Every time there could be a return value. The return value do not necessarily put on stack, put on registers. You need to find a way to implement or place global variables, local variables. Global variables are in .ro data or .data. Local variables are on stack, okay? The local variables, if you analyze an L file, you cannot find local variables because they are not in the L file. They're dynamic. They only exist when you execute this on stack. Then sometimes there could be some temporary variables. And also there is a return address. That's actually quite important. To achieve that, you also need some simple function frame pointers or previous function pointers, which we will take a look later. So let's start with simple things, okay? So let's start with global and local variables. Okay? So variables that are declared inside a function or block in C or C++, they are called local variables, okay? They can only be used by the statements that are inside that function or that block, right? So local variables are not known to functions outside their own. Then we have global variables, which are defined just in a C file, maybe usually at the beginning of the C file, and they are outside a function. So global variables hold their value throughout the lifetime of the program, and they can be accessed in any function in this program, right? So that is the C definition of those variables. But how do you implement that? How do you really achieve this in the compiler, right? So parameters are actually kind of like local variables. So we skip that for now. So now we look at a very simple example. It's called global, local v, global and the local variables. We have a main function. The main function has two arguments here. The first one is an integer, the second one is a pointer. So this actually is an array of pointer. A pointer to an array. Then we have two local variables. I mark them as L means local. Right. Two local variables. Then we have two printf functions. The printf function is trying to look for two global variables. One of them is type is integer, another one is unsigned integer, but that really matter. Okay. So what we do here is we print out the address of those global variables. And also we try to print out the address of the local variables. Okay. After that, we call function func. The function func take one parameter, which is an integer. Then two local variables, one initialized, one not initialized. The global variable, the same thing, one initialized, one not initialized. This one is actually a pointer. So this global variable, if you program your C, you need to understand that this global variable G underscore I doesn't really have the string itself, okay? It only has an address of the string. Then we have another pointer GU here. Then in this function, we print out the address of everything. So if we run this program, what do we expect to see if we run this? First, we can see the symbols of this. There are not so many symbols here. What we find here is you find some function names and type here is T in text. So how about the variables? What do we find? We only find two. G underscore I and G underscore U, okay? The global ones. The symbols. We do not find the local ones because we don't have an address. They're dynamic, right? So if we run this program, we run this program, this is 32-bit version. And let's say the address. The GI is at this address, starting at 56, okay? So kind of it's the middle or the bottom half of the 4 GB address space, right? Because the whole address space is from 0 to F, right? 4 GB. This kind of like the bottom half. Okay, those two global variables. Then those two local variables in main function, and also the other two local variables in function, they have the same name, okay? But doesn't really matter. There is no conflict, even if they have the same name, because they have different scope, right? Those two, their scope is in the main function, those two in the func. So the main function, which function executes first? The main executes first, main calls func, then func returns to main, so main keeps executing, right? In this case. So then the stack goes from high address to low address. And the local variables, so when main calls func, we will first have main's local variables. So they are supposed to add a higher address. Then we have the function of func, and their local variables will be a lower address, right? So first of all, the stack is at a quite higher address. It starts at FF. It's almost at the top, okay? Almost at the top. Then LI is at the address of ABC. The LU, the second variable, has a lower address at AB8. That's a lower address than ABC. Then we call function func, which goes A8C, even lower, right? Then LU, ABB. Now we have another one is a P, which is the parameter of function. So that one is at AA0, which will be actually here, right? It's lower than the local variable of main, but higher than the local variable of func, right? So you can consider that it's kind of like the local variable of func, but before the real local variables. So those are the addresses. So yeah. So for this one, we're not using the heap. Okay. Heap's address will be somewhere usually. First of all of those can be randomized. There is a security feature to randomize everything. If we are talking about the picture we saw last class, the heap it probably will be placed higher than this. Maybe something like 7 something, 8 something, somewhere there. So if we go to the 64-bit version of this, we see something similar, right? So GI, GU, they're still at 5555. Okay. Bottom half of the huge address space. The stack is at somewhere high, but not that high. Okay. Because that's because for 64-bit machines right now, we're not really using the full 64-bit version. We're not really using the full 64-bit of address space. Right now, we're using something like 39-bit, I believe. I'm usually using 39-bit, because we don't really need 64. It's too big for us right now. So the stack is at somewhere like 7F, but the trend is the same, right? It still goes down. main, the local variables of main is going to 786, 788 going down. And this one will be 756, 758 goes down. And this one, 746. This one is a different story because in 64-bit, this one doesn't really go to the memory. You will go to the register because we have many more registers there. In 32-bit, we use the stack to pass parameters. In 64-bit, we first use registers to pass because it will be faster. Register stack is on memory. Memory is not part of the CPU. It's slower than CPU. Register is a little bit faster. Okay, so what information we really need here? We need code. Okay, that's the dot text section. We need the parameters. For 32-bit, we use the stack to pass parameters. 64-bit, registers first. If registers are not enough, we use stack. Return value, we put in EAX in 32-bit or RAX in 64-bit. That's where we put the return value. If the function returns 0, then the EAX will have the value of 0. Global variables go to BSS or .data section. Local variables could be on stack. We could also use registers to do that. Temporary variables, same as local variables. Return address, this is a very interesting one, also goes to the stack. And the stack is part of memory. That's why what we're studying in this class is memory corruption attack. If we corrupt the memory, we can overwrite important control information or other information. The return address is a very important control information. It controls when this program, this function returns, what is the next instruction to execute. If we override this, then we can ask the CPU to execute our code instead of originally it's supposed to return. Function frame pointers will be use EVP, RVP to do that. What do you mean? It doesn't really matter. So when you're talking about asynchronous call, I'm thinking about something like a callback function, right? Something like that. I'm not sure what you're talking about there. Yeah. Okay. Like 2 threads. Okay. There will be a lot of return addresses in a thread or in a program, because each function, there will be a return address. If you overwrite any of those on stack, so first of all, the return address is not part of the code, right? It's part of the stack. So it's runtime data. If you overwrite any of those runtime data, and whenever that is used, you will be able to control it to go anywhere. Yeah. Many addresses. Yeah. No, they are not on registers. The return value is unregistered. Yes. Yes. Well, at one point, you only need one return value, right? When you are executing this function has a return value. Later, you're not executing the more, so it doesn't really matter. They do not really happen at the same time. That's his point, right? So they just time sharing the CPU. They're not really happening at the same time. Yeah. It's the happening at the same time is an illusion. Yes, but if we have multiple cores, multiple CPUs, then it's a different case. Yeah. Okay, so stack obviously is a very fundamental data structure, and we use this similar similar structure in all kinds of platforms. Even if in the future you work on MIPS or ARM, you will face the same thing. But usually it starts at a higher address and goes to a lower address. Some architectures will implement a reverse way, but most of right now implement a high to low. So functions are free to push registers values onto the stack or even pop them. Some important hardware registers and instructions on x86 for stack is ESP 32-bit or RSP that always points to the top of the stack. Okay, always points to the top of the stack. But here, top of the stack is actually a lower address because the stack goes lower. Then several instructions, the push instruction and pop instruction. Push takes one operand. Let's say you want to push EAX. It means you are going to first decrement the stack pointer. That's the first step. You decrement that, then you store the value in EX to the location that ESP points to. Okay? That's how ESP always points to the top of the stack. Always point to the top item on the stack. That's for this architecture. Some architecture do it in another way. They will push the value first, then decrement that. That's also possible. Some architecture do that. But in that case, you always point to the empty space on top of the last item. But in x86 and the ARM, we don't do that. Okay. Then pop, where simply stores or copy the value at the location ESP points to back to the register. Like to pop EAX, then whatever ESP points to will go back to the register EAX. Okay. Then it will increment the stack pointer. That's it. It doesn't clean the stack. Whatever on that previous location, it's still there. It doesn't reset it. Okay, it's still there. So that could, from security point of view, that could be some information leakage, vulnerabilities there. Next, we are going to look at each of those instructions more closely, because without understanding those instructions, you will not be able to hack this. Okay? Push, pop, call, return, enter, and leave. Those 6 instructions. Enter and leave is equivalent. They are equivalent to several instructions. So you don't really need to understand. Remember those two, but the sequence of instructions, that's what you need. Okay. Let's say a little bit animation here. This is what the memory look like. On the top is a higher address, lower is lower address. We have a value Z here, Y here, X here. ESP or 34-bit RSP points to this X value. So this is the top of the stack right now. Now we run the instruction push EAX. What happens is ESP first move from here to here. Then the value of EAX is moved to this memory location. Okay? This is the register. This is the memory location. So this is what we get after we execute this instruction. The reverse operation of this, ESP still points to X. Now we pop EAX, then what ESP points to goes to the register EAX. So now the EAX has a value of X. Then ESP will increment 4 bytes. Now it points to 1. But X actually is still here. No one thinks that. Right? Still here.
Why?
Because the hardware is not doing that. From There is a security issue in that, but from the instruction set design point of view, you want the instruction set to be fast, right? It's only does the things that makes the system run. Security is not the first citizen when you design a system, right? But if you want to do something like this, you want to clean it up, then you do that at a software layer. Basically, you instrument a lot of instruction after this. You need a lot of instruction to do this. The pop instruction itself doesn't do that. Okay. One of the very interesting instruction, the call instruction. Here, does anyone remember what I call this? It's called call EX. What's it called? Direct call, indirect call. What's this? This is called an indirect one. Okay, because the operator here is a register, so we don't know the value of that when we do a static analysis. Okay, only when we run this instruction, the value of EAX has been computed, so we know where our target is. If we are making a function call in some other code, then that is actually hard coded. This one, we don't have the value. So here we have, this is the code, right? And for code, this is a lower address, this is a higher address. So this is the sequence we're executing. We're executing this one, this one, this one. This is the code. This is the stack. This is high, this is low. Before we execute this instruction, the stack and code look like this. ESP points to X. EIP points to the instruction called EAX, which means we are about to execute this instruction. Before that, we already execute push one here. Next, we're going to execute pop. Well, actually, next one, we're not going to execute pop. Next one, we're going to execute whatever at EAX, right? But after we return, we're supposed to return. For call, we're supposed to return. When we return, we are supposed to keep executing it. So what this call instruction does is two things. First, it pushes the address of the next instruction to the stack. So it pushes the address of pop DBX to the stack. Okay? The stack was like this. Now we're pushing something else. So we're going to push the address of pop DBX here. The ESP points to this. Just ignore this percentage sign. That's for the AT&T syntax. Okay. So many years ago, when I teach this class, I used AT&T syntax. And then I switched to Intel syntax. Yeah. So that's the first thing. So the reason we're doing this is we want to remember eventually where we want to return to. And we want to return to here, right? That's why we want to save this address. So this one is called the return address. Now, after that, we're just moving whatever the destination address is. In this case, the destination address is EAX. Move that to EIP. So EIP will have the value of EAX in this case. So the EIP, after this instruction, will not go sequentially to here. You will have you will have the value of EAX. Okay. So that is how we make a system. We make a function call. The reverse operation of call is return. And this instruction doesn't have to have an operand. It can have one, but it's to balance the stack. It's not really showing the destination. So this instruction doesn't have a destination. This is different from the call instruction. Call instruction has a destination here. This one doesn't have a destination. This one will always use what ESP points to as the destination. That's it. Whatever the ESP points to right now, when you execute the instruction, is the destination. So this is the code. We have this program running there, the function running there. Now we reach the end of it, which is return. After that, doesn't matter because we're going to return. We're not going to execute the next one, right? Then ESP in this case points to the value X. Then this will simply do a pop of the value X to not to the EIP. So the CPU is going to execute from the address of X, and the ESP will move up 4 bytes. That's it. So you can consider this return instruction as a special pop instruction. Different from pop. Pop has a destination. Here the destination is implied. The destination is EIP or RIP or 64-bit. So this instruction directly changes the control flow of the program. Any questions?
What is EIPI?
EIP is the instruction pointer.
Mhm.
Is so on other architectures, it's also it could be called like PC, program counter. That's the address of the next instruction to execute. Basically.
Yeah, I read the mapping. Gotcha.
Yes. For example, in this case, I'm showing before, right?
Yeah.
So before we execute this, EIP points to this instruction. This is the which means return is the instruction we are about to execute. Make sense? Instruction is in memory, not on stack. Instructions are in those instruction sections, including .text. That's where your code goes. The C library code do not necessarily go to .text, go to other sections. Yeah. No. You can't, technically you can put code in heap, but that also have security problems. Yeah. So here, most of the code we're talking about, they are generated at a compiler time. Their sections were determined at a compiler time. It's very possible, like some malware, they always use these techniques. They were generated code at a runtime. So if you analyze a piece of application or software or malware at a static time, you do not really see those malicious code because it hasn't been generated yet. Generated here would be something very simple like decrypting. Then after they at runtime they decrypt that, they may put it anywhere, not necessarily put on .text. They don't want to put it in .text because they don't want you to analyze it. It's possible, but in these cases, we're talking about the standard ways to do things. So the next instruction is enter. You may not see this enter instruction a lot in this class, but you will see those 3 instructions a lot in your class. Those are equivalent to enter. Those 3 instructions are push EBP, move ESP to EBP, then subtract some value from ESP. Okay. So those shoes appear a lot in the beginning of many functions. So that's why they're called the prologue of functions. They're basically setting up the stack, setting up the stack frame for a function. Those are the something we're going to attack. Let's say for those 3 instructions, the stack looks like this before, right? ESP points to somewhere and has a value X. The first instruction here we have is push EBP. So the value of EBP will be pushed to here. Okay. ESP points to here. Okay? That's the very first step. So after that, we're going to move ESP to EBP. What does that mean? The EBP value is overwritten, right? But the old EBP value we already saved it in the previous instruction, right? Because we saved it, now we can override it. Now the ESP now points to the save EBP basically, because EBP and both EBP and ESP are here. Now we move ESP, both of them to EBP. So EBP points to here. Now we subtract some numbers from ESP. Then ESP goes down again. ESP points to somewhere here. EBP points to the old EBP, and then here we have some space. This step is to reserve local variables This is actually allocating the memory locations for local variables. Yeah. Global variables, they are already allocated in dot data, dot read data, whatever. But local variables, they're actually allocated by this instruction here, subtract. We will see more examples later. So we're going to revisit this multiple times until you guys understand. So this is just one. Yeah.
Why do we need one variable?
It's long story. From right now, you probably cannot see it. Easy way to explain this is a function will call another function. That function will call another function, right? Which means eventually all of them need to go back to the previous function that calls it, which means there is a return address associated with each function call, not associated with each function call. This is a dynamic thing, right? Then you need to save that information, and you save that information on a stack. And for each function call, then you have a simple data structure here to say, oh, this is the return address, those are the parameters, and this is everything. But that data structure, they are on stack. They go down, they grow down. Then you need to know where is the data structure for the previous function. And that EBP basically points to the data structure for the previous function. So now we're making a new function call, and we need to save the function that calls, this function calls that data structure. That's why we're always saving this. So right now it's a little bit high level. When we say more concrete examples, like the full function, one function code, you will understand. So leave is the reverse operation of under. It only has two instructions. Move EBP back to ESP, then pop EBP. Let's say this is the end of the function. We're going to leave. After leave, we're going to do return, right? So here we have ESP is here. EBP points to here. So now the local variables, we don't need them anymore, okay? So what we need to do is we move the value of EBP to ESP. So ESP will point to here as well. Then we do a pop EBP. So what's saved here goes to back to EBP. Okay. Then it will look something like this, and the EBP will have the old EBP value. So basically, we restore everything. There will be more concrete examples. This is the first time you look at this, so I do not expect you to understand why we are doing this right now. So a concept here is function frame. That is the data structure I was talking about, right? So functions would like to use stack to allocate space for their local variables and also save other things, right? So we will use the stack pointer ESP for this. So the function pointer, the frame pointer, points to the start of the function frame on the stack, and then each local variables will be referenced by an offset of that function frame pointer, and that frame pointer will use EBP for that. To remember this, you can remember that's a base pointer, okay? Extended base pointer. Yeah. We will see more examples of that. Let's keep those concepts. Okay. Calling conventions. For a same piece of C code, for the same piece of function, the compiler can make different choices to implement that. And the different compilers can make different choices. That's why we need to have some standard or conventions. The code generated, compiled by different compilers can still call each other. And in function call, that is called the calling conventions. So the calling convention basically defines how parameters are stored on the stack, in what order, those kind of information, and who will store those information. Is the caller function to store that, or the callee function to store that? Obviously, this is related to the CPU, related to the operating system, related to the compiler. And there are many different choices. That's why we need a convention or standard. So The standard needles calling convention is this. It's also called the standard say declare or say standard calling convention. So the caller in this case will do these things. Then the callee will do these things. Besides the business logic of the function, right? So the caller will first push all the arguments onto the stack. I'm talking about 32-bit, not 64-bit. Okay, push all the arguments to the stack, but in the order of we push the rightmost parameters onto the stack first. Then we go left. Okay. If there are 6 variables, we push the 6th one first, then the 5th one, 4th one. After we push those onto the stack, the caller will execute the call instruction. It has those 2 steps we know. Then the callee will push the previous string pointer onto the stack, which is the EBP. That's the instruction we saw just now, the push EBP. This is the callee's job to do that. That's why we call this is a prologue of each function. Because at the beginning of the function, the callee is supposed to do this. Okay, that's callee's job. That's a standard. You can implement it a totally different way as long as your function do not call other library functions or no one calls you. Okay. You can implement your own compiler. But this is the standard. Then you will set up the new string pointer, which is move ESP to EBP. Right? Just one instruction to do that. Then create space on stack for local variables, which is subtract some numbers from ESP. Now after that, when it returns, you should make sure the stack is consistent as when it is called. That's why we have the move EBP to ESP, then pop EBP instruction, those 2. So after that, you make sure the return value goes to the EAX register. Then it will just execute the return instruction. Okay. So which means here, the return value can only be 32. It cannot be bigger. If you are returning something bigger, you need to use a pointer or something else. Or you can use a parameter of a pointer to do that, right? To bypass this. A lot of functions actually use that. They just use the return value as status. What is the status of the function? It's successful, it's not successful. The real return value is not really in the return value. It's in somewhere in the memory. There's memory to do. So we already saw those functions, those instructions. Those are what callee does to allocate the stack. That's why it's called the function prologue. Happens at the beginning of the function. Push EBP, move ESP to EBP, and subtract something from there. To deallocate this, it's just those 3 instructions: move EBP to ESP, pop EBP, then just return. Now let's look at this. Do I have animation for this? Let's take a look at this. We try to understand as many instructions here as we can. Okay, this is a function. Yeah, go ahead.
Start of the program.
What?
At the start of the program process, EBP and ESP are the same.
No. So EBP at the start of a function, right? The EBP still has the string pointer of the previous function. Because this function is called by someone else, right? It has a previous function's string pointer. Yeah. ESP points to wherever the top of the stack is. They will not be the same. Yeah. At a high level, I mean, that's my explanation. But when you say more concrete examples, you will know. Let's say, you said we have 430? Yeah, only 430.
I think so. I see people being in the window right now.
If we have 430, then I would say we stop here. Then come back next. Yeah, 430. Okay. Then we will talk about this next week. I do want to show you guys homework 1. Homework one has already been posted. It's here. There are 6 questions. First, actually 7 tasks. First, you need to read the academic integrity policy, find it by yourself. After that, you need to read the syllabus. There is a secret embedded in the syllabus. You need to find it. Right? You already find it? No. Okay. Then register an account on our server. Then there are several homeworks to do. Those are very easy ones for the first week. Yeah, very simple. I already showed you the demo of everything. Yeah. So if you are unclear how to do that, just go back to the videos. Okay. Yeah, the first week it's kind of easy. Next week we are going to have several hacking challenges. Yeah, I don't really have a TA for this class. So when you guys ever you need something, just ping me on Slack. We can meet online. We can meet in person. Sometimes I actually prefer to meet online because it's easier. We can share screen. I did that during pandemic. It was very convenient. For the CTF midterm and final, I try to make it easier. The challenges will not be easier, but I will try to give you some hints during the exam. So I will be walking around to give you hints. Not necessarily help you to do that, but give you more hints there. Because I figured some of you are actually online students, right? And this will be a challenging class for you, but let's be a 1 semester hacker. It will be a lot. Okay, cool. Sounds good. Okay, then see you guys next week. Next week we are going to say our first hack. We will get the real flags next week. Yes.
All right.